Okay, so finishing up this unit, but before that, there's ICAL out. This is the last normal ICA, and then before the final exam review ICA. So this is just like the midterm review ICA. It's a little bit longer, and the midterm ICA is available as well. That's the A version here. If you want it just as a practice, just looking into the final exam, which will be comprehensive, but mainly biased on the final exam or the post midterm content. And so that's what we're kind of saying down here. After this one disappears, which will be right when lecture M starts, then there'll be a practice version of this one, which is released as well. So you'll have all of that content if you want that available looking into the final exam. There's other resources available. Look at that final exam module. You have to take that lockdown browser compliance test first, and that will unlock that module, and then you can get access to a bunch of prior exams and other resources. So that's on Canvas. Homework J2 is out. That's the last homework. It cannot be dropped because we collect some metrics on it. It also won't have a solution set. It combines kind of lecture and lab content together. It is an inventory management problem. So it's a problem that I think you've seen before that you're going to be modifying in certain ways and then doing some analysis that will relate to steady state and transient simulation and just generally showing that you can make some relatively minor modifications to arena logic. So that's what's going on there. This lab schedule. So because of Veterans Day, I would normally give this lecture last week. So that's why this is phrased in a way that sort of suggesting that lab is due this weekend. Lab was technically due this past weekend, but remember that the availability is up through this weekend. So you might it might say right now it's overdue, but I've given you basically 2 weeks. The target was last weekend, but if you turn it in any time between now and next weekend or this upcoming weekend, then there's no penalty. So that's because this lab 10 is basically 2 labs in one. So there's a bunch of extra bonus points, 20 bonus points possible, or 20 bonus points out of 30 total. So there's 50 points possible, 30 regulation plus the 20 bonus. Because of Veterans Day messed up the calendar, I might go ahead and add a couple of days to this, making the availability go out to Wednesday, just to provide a little extra time, if that'll help. So if I don't do that, someone remind me, and I will make sure to do it. But that's my intent, is to extend this from Sunday to Wednesday of next week. So that's the plan. It's on video. So I always get a lot of emails about these things that we announce in lecture. And so just, it's in lecture here, and then, so that's the intent there. So if you don't see that availability window move, just send me a note, and I probably forgot, and I'll make sure to shift it. Otherwise, no other labs. So the rest of the lab time is focused on the final project. Final project here. The feedback coming back from the input modeling thing, a lot of it, most people actually have probably gone too ambitious in some cases, like studying like a lot of decision variables and all that. And I've tried to give the feedback that just pick one of them. Like if you're picking, if you've figured out that there's 2 different ways we could organize how an order is put together at a restaurant, then rather than studying that and cashiers and all these other things, just focus on the one thing. It's a small project, and all you really have to do is sort of say, is there a difference between these, an as-is system and a proposed change in the system? That's a fine thing to do. You don't have to optimize over every possible decision variable. So, but you do want to make sure that it's complex enough to warrant a simulation. So if you find that the only input models that you think you need are inter-arrival time and service times, you might be just simulating a queuing node. And if it's just a single queuing node, we don't really need a simulation for that. There's not really a lot of complexity there. If you find yourself asking, will adding cashiers reduce waiting time? I think the answer is always going to be yes. It's probably not going to increase waiting time. So again, that's just from basic queuing theory. That's just coming out of 470. These are things that you should know about capacity of resources and how that affects, the qualitative features of how long lines are and things like that. You don't need a simulation for that. Now, if you start getting into trade-offs, like I could add a cashier or I could add an ordering kiosk. And based on the space in the restaurant, I can only do one of those. Which one is going to be better? And here are the trade-offs. So the cashier takes orders faster. The kiosk, I don't have to pay for the cashier, but it breaks down periodically. So you have those things you kind of have to balance. I'm trying to avoid doing this, but you have to have those things you kind of have to balance, and then that and then that would be a great thing to look at in sim, because it's not obvious for this particular spot which one of those would be better. So if you already kind of know what the answer is going to be, and a simulation result that would go the other way would sort of flag things. You're like, oh, there's something like if it's possibly the case that what you think is true, if the sim told you something else, that would give you evidence that your sim is broken. Like if your sim really can only go one way, then there's no reason to run the sim. So it has to be something that it's like there's an argument that it could go either way, and I'm using the sim to break that argument. So that's what I mean, is it kind of complex enough? And it usually will that involve enough blocks in your model that it's going to feel natural that there'll be a certain section of it, like the order process, like the processing order stage. Like imagine that if you're like in a restaurant, you've got you take orders in, you have to process the orders, and then they get then the orders get delivered to the customer. And there might be a little bit of logic in how people are coming into the restaurant, but if the major module you're changing is like a bunch of blocks in the middle, that could be, you could say, I might imagine that to be a submodel, that I'll put all of that in a submodel. And then in my as is system, I'll have one submodel. And in my proposed system, I'd have a different submodel. So that's kind of like the heuristic we used to use is, is it complex enough that it has enough blocks that you could put them behind a submodel, and that it wouldn't just be like the submodel has just one block inside it. Like there would be a justifiable reason for why you created a submodel. But the biggest thing I'm really focused on is, was it really necessary? So I used to have people, the students present in class, and then I'd have some of the other IE faculty come and sit up here, and then they would end up being the ones filling out the presentation evaluations. And that would always be the question. You have a random, wrong pan, or somebody would be in here, and then they, would always ask, well, why did you need simulation for that? Like it wasn't that obvious. So you don't want that question. So that's what I want, should be drive your final choice of your study here. And you can shrink things down. It can be one or two decision variables, just as long as it's not clear how changing that decision variable will change the outcome. And that's the reason why you're simulating. That's the goal. So that's all culminates the last week of class, Wednesday of the last week of class. Upload these to Canvas. We're not presenting them in class. They're just uploaded to Canvas. And so 10-minute presentation, 4-page report. And then between Wednesday and Saturday of that week before finals week, you'll watch one of those videos, you'll read one of those reports, and you'll fill out your own peer review. And that's the plan there. So any questions? Yep. Well, for one, the enrollment for this class was so variable that it was very difficult for me to plan how many classes I would need to do the presentations. Also, then you say, well, why don't you do them in labs? And but even the lab numbers, like some semester we would have 3 labs, some semester 2. So it became, and then just in general, it became kind of, I could tell that I don't think a lot of students were getting a lot out of it, because it's kind of excruciating, watching these one after another. So so I realized we could make it. So what I did instead is I added those review sessions. So that was the trade-off there, is that those extra classes that I used to use to present, I could now use them for something else rather than cramming in more lecture content. Then I added the review sessions. All right. Okay, so let's start with a clicker just to get us warmed up from last time. Multiple choice. Question is here, a point estimate. If somebody gives you a point estimate, if they say the waiting time is 5 minutes, and that's an estimate. So a point estimate is equivalent to what type of confidence interval? A 0% confidence interval, a 95% confidence interval, a 100% confidence interval, or has no relationship from a confidence interval. So go ahead and put that in there. Give you a few more, maybe 10 more seconds. All right, let's see what some of the results are here. Okay, so it looks like we're getting a lot clustering around 0% confidence interval and a few others on the rest here. And so, yeah, that's wisdom of the crowd. That's what I was looking for, is this 0% confidence interval. I'm gonna go ahead and hit stop. And so you can think about the width of the confidence interval is proportional to the confidence. So a 0% confidence interval collapses to zero width. A 100% confidence interval expands to the entire number line. So a 95% confidence interval says in 95% of all the universes where you ask me this question, the right answer is within the estimate that I give you. And so I might be unlucky to be in one of those 5% universes where the interval I give you is totally off, but 95% of the universes I'm not. So that's good enough for me. So if it's not good enough for you, you can go to 100% and you can say, but the only way you can be 100% confident that the real value is within the estimate you give your stakeholder is if you tell them it could be anything. So a 0% confidence interval, if you tell somebody the waiting time is 5 minutes, all you're telling them is at the end of this particular simulation run, the average customer waited 5 minutes. It doesn't tell you anything about the average customer in real life. So you really have to say is based on the variability that I see and the number of replications that I ran, the waiting time is between 4 minutes and 6 minutes. And I'm 95% sure that the real waiting time is within that interval. So that's how we interpret confidence intervals. Okay. So flip back here. All right. One more related to that. Clicker. All right, so this is another multiple choice. Okay, so assuming similar estimates of variance, of standard deviation in the populations, and I look at these three confidence intervals. So I've got the same population, let's say the same simulation, but I've sampled it a different number of times. And so which of these confidence intervals, A, B, or C, where A is intermediate, B is smallest, C is largest, which one of these confidence intervals corresponds to the largest number of samples, given that the variance is the same across these? So go ahead and clock in your answer. Or in other words, as systems become more variable, what happens to your confidence in the estimates? So let's see where we are. All right, so we have, looks like I'll go ahead and stop now. All right, so it looks like we've got a big cluster around B, and then a little side lobe around C, and then almost nobody around A. It looks like most people prefer B, I'm guessing because that's the smallest, and that's what I was looking for. So it's this idea that as you gain more samples, you get higher resolution, you get higher sensitivity, which means your estimates are better. So for the same percent confidence, you can say, I have to be 95% confident. So I have to be, in 95% of the universes, I'm going to give you an answer that includes the right answer. Well, if I have more samples, then I can zoom in a little bit more so that 95% of the time, then my answer will be in this tinier interval. So that's why we sample more. We sample more to shrink our confidence intervals. That's the idea there. All right, any questions about those concepts? Okay, which then dovetail into what we are talking about today. So So we talked about this, like what is a confidence interval? If you take a t-test, so this is the expression that you use when you do a t-test, you can basically solve for theta, solve for the hypotheses. And what this will tell you is for this particular t-test, what range of hypotheses would have been rejected and what range of hypotheses would fail to be rejected. And so if your hypothesis is not in the confidence interval, then that would say that a t-test with these data would reject it. If your confidence or if your hypothesis is in the confidence interval, then that is saying that a t-test with these data would fail to reject it. So that's our interpretation of what a confidence interval is. And with this confidence interval, we're going to frequently just use the term half width or H. So what is H? That's just half of the confidence interval. That's this formula here. And this formula here is just the standard error of the mean scaled by that critical t value. So if I give you a confidence interval and I tell you the number of samples, you should be able to look up in the back of the book a critical t value and convert it to other confidence intervals. So you should be able to convert a 95% confidence interval to a 90% confidence interval. You should be able to back out what the standard error of the mean is, and you should be able to back out what the standard deviation estimate is. So you can get a lot of information from a confidence interval. Okay, so what can we do with a confidence interval? So these confidence intervals, keep in mind, these are basically one sample t-tests. So they are sets of hypotheses that either fail to be rejected or are rejected. And so the one sample rule is that if the confidence interval includes the mean, then or does not include the mean, we reject it. Otherwise, fail to reject. So that's all that we're kind of summarizing down here. It's a review from last time. And what that looks like is if we have 100 experiments, so that's what this is, 100 experiments, another 100 experiments, another 100 experiments. This is in where we decided to do 20 samples. This one, we decided to do an experiment with 200 samples. This is our experiment with 2,000 samples. All three of these cases are 95% confidence intervals. But what we see is that, so in all three of these cases, when you run, imagine these are 100 universes in this case, 100 universes in this case, this 100 universes in this case. And so in this multiverse, we have 5-ish, so about 4 here. We have 5-ish unlucky universes who ran bad experiments. Same thing with this one. We have only 2 in this one, but roughly around 5. And then here looks like we have 6, again, roughly around 5. So for those 100 universes, so in this multiverse scenario, there are 5 universes in each one of these multiverses where you have an unlucky scientist who's run this experiment and has gotten a result that doesn't include the real result. So in all 3 of these, most of the experiments do include the real result. But the difference here is that in this multiverse, then the confidence intervals are much wider than this one. So they have a much higher precision estimate in this multiverse than in this multiverse. And that comes from the extra sampling. And so why don't you sample like this all the time? Because it costs money to sample. So in a real experiment, it might cost $1 million per replication or $10,000 per replication. In a computer simulation, it usually costs time, and time is money. So you might need to schedule time on a high performance computer to run your simulation, and you only have a certain number of hours that you're budgeted. And so hours, connects to number of replications you can run. So more samples is more power, narrow confidences. The other side of this is more variance is less power, wider confidences. So same idea here. Now I've got 30 samples across all 3 multiverses. And but in this multiverse, the process that's being sampled is a low variance process. It has less variability. And this multiverse, the process being sampled, the simulation has high variability. So in all 3 multiverses, you still have roughly around 5 universes where the experimenter misses completely the estimate. But the big difference here is that you have tighter estimates with lower variability. And so this tells you 2 things. If you can't get rid of your variability, you probably will need to to buy down the variability with more samples. So variance is money as well. So if I need a tighter estimate than this, and I need it to be 95% confidence, then that means I'm going to have to pay for more replications. But if I have the ability to do something to my experiment to control for sources of variation. So if I notice that whenever my computer is running hot, then I get waiting times that are a little longer because of some weird issue with the random number generator. And over my computer is running cool, I get waiting times that are less, that are shorter because of some weird, and probably problematic issue with my random number generator. I can control for that. I can use the temperature of my computer to subtract off the variance generated by the temperature of my computer. And that allows me to, with the same number of replications, shrink these intervals. And that's what we're going to learn how to do next unit. So starting in the next lecture. So that's the idea there. Now, what else can we do with confidence intervals? Confidence intervals show up even though we don't, as you get into more advanced statistics, you don't use t-tests and ANOVAs directly as much. You shift into using linear regression. But the way we interpret linear regression is often with the good old-fashioned t-tests and so on. So here's an example from a paper from a colleague at University of Arizona. It turns out that there's, for across animals, the more mass you have, the more energy you use, which makes sense, but you might expect it to scale linearly. So if an elephant is 1,000 times the weight of a mouse, you would expect an elephant to use 1,000 times the energy of a mouse. But it turns out that's not the case. As you get bigger and bigger and bigger, you use less energy per unit mass. And it tends to be for big organisms, for organisms like you and me, that aren't groups together, that it scales what they call as a power law with a 3/4 exponent, a 0.75 exponent. And that just is like across nature. It's one of these interesting rules of nature. And so what this colleague at the University of Arizona was studying was, what about with ant colonies? And so if you make you can measure how much energy a colony uses. You basically can collect the carbon dioxide that's produced by a colony of ants. And then you can use that to figure out how much energy the colony is using. And then you can study whether the small colonies use less energy than the large colonies and to what extent. And if it falls on the 1-to-1 line, then that means that, well, okay, you have twice the number of ants, you burn twice the number of calories. And so it's linear. But if it's like this thing that happens at the organismal level, then you might expect it to be lower than that. And so what she did is she put, in this case, it turns out if you take the logarithm of colony mass and a logarithm of how much energy they're burning, metabolic rate, then you get points that fall on a line. And this is just something we already know. And so you can use linear regression to fit that line. And so you fit that line, and the slope of that line right there tells you that exponent that I was talking about. If it's a 1.0, then that means that if you double the mass of the object, you're going to double how much energy it uses. And her point estimate is about 0.78. It's close to that 0.75. Now, you don't end there. So with linear regression, you then say, well, what's the confidence interval of the slope? So this regression coefficient, you then say, okay, actually, and she reports it down here in a paragraph, that this confidence interval, it has a 95% confidence interval of 0.67 through 0.9. And that's what I've shown up here. So 0.67 through 0.89. So she's saying, I don't know what the actual slope is for these ants. But what I can tell you, and this is exactly what she says in this paragraph here, is that 1.0, which would be the double the ants, double the burn rate, that's outside of the confidence interval. So we have rejected the possibility that ant colonies scale additively. So if you double the ants, they're actually scaling less than that. So something's happening as you add more ants that makes each ant use less energy. Very similar to processes that we think are happening as you go from a mouse, which is burning lots and lots of energy per cell, to an elephant, which is burning very little energy per cell. She goes on to say that, oh, by the way, notice that 0.75, so we have mathematical theory, which predicts that it might be 0.75, is inside the confidence interval. Now, she's not saying 0.75 is it, but she's saying based on these data, I can reject one, but I can't reject 0.75. So it is consistent with the hypothesis that ants are scaling with the same theory that are used to understand mice versus elephants. So that's confidence intervals applied to slopes, applied to regression coefficients. That's often how we interpret linear regression models with t-tests on slopes. And we can see that. So this is actually a study that came out a couple days ago. I thought it was kind of cute, so I threw it in there. Greeting vocalizations in domestic cats are more frequent with male caregivers. So this study, they used Bonferroni correction, all sorts of things I could have, spent time talking about, but I just picked this one thing out. And they said that there's a bunch of things that cats do when somebody opens a door and greets their cat. So they put a bunch of GoPros on caregivers that had different, some were men, some were women, some were young, some were old. And then they had cats, and then cats had all sorts of different properties. And then they used the GoPro to measure lots of different things. And here we're focusing on the vocalization the cats make within the number of vocalizations the cats make within that 5 minutes. And they did a linear regression. They did a regression model with all of these predictors inside here. And so most of these are discrete predictors. So this is, if you go from the baseline was a female caregiver. So if you go to a male caregiver, is the cat, the baseline was a female cat. So you go to a male cat and so on. And what we see here in all of these predictors that might explain the extra purring that you get from the cats, all of these predictors, those slopes there, that's the estimate is on the outside of the brackets. Inside the brackets is the 95% confidence interval. Those confidence intervals all include 0. And so these confidence intervals that all include 0 correspond. Here's the t statistic, and here is the p-value. All these p-values are greater than 0.5. And so all of these predictors are not significantly different from 0. In other words, you can't exclude 0 for these predictors. You can't exclude no effect. But the one effect that they did find, that this confidence interval is bounded away from 0. So the slope, so in this case, because it's discrete, it's the average number of extra calls you get in 5 minutes for whatever reason is on average for these data, it's 2.93 calls. So 2.39 calls. And so the idea is if you have a male caregiver versus a female caregiver, on average, when the male caregiver comes in, the cat is going to have, on average, 2.39 more calls in that 5-minute period. And based on all the variance they got across all the caregivers that they studied and all the cats that they studied, so there were 26 cats involved in this, then they said, well, 2.39, that might not be the actual average, but the actual average, we're 95% sure, is between 0.27 and 4.52. So that has a significant t value from a t-test, so it's less than 0.05, so that's a significant result. So that's why they titled their paper, Breeding Vocalizations in Domestic Cats Are More Frequent with Male Caregivers. That line right there. And this is a common way to summarize these regression models. In fact, a lot of times people skip the T and the P. They just list these confidence intervals. And it is up to the reader to know that if a confidence interval includes 0, it's not significantly different. And if it excludes 0, it is significant. And 0, why 0? Because in a linear regression model, 0 is no relationship. It's a flat line. Anything other than 0 is a positive relationship or a negative relationship. So that's how you interpret that. So you should just be trained to, when you see a confidence interval, if it's a linear regression coefficient, so if it's a slope, look for 0. And we're going to see that a lot as we start moving forward in this lecture and some of the next. All right, questions about this result? See what I mean? How you use t-tests to analyze linear regression. And you do that through the lens of the confidence interval. Okay. All right. So, other things we do with these one sample confidence intervals, if you have two confidence intervals, so you have a confidence interval of, for example, the number of calls that if you have a group, if we did that, a simpler version of that study, and we had a bunch of female caregivers who enter, and we measure this with their cats, and a bunch of male caregivers who enter, we measure this with their cats. We take a one sample confidence interval of the number of calls the cats make for both of those. If those two confidence intervals for the female caregivers and for the male caregivers, if they are disjoint, so in other words, if the male confidence interval is non-overlapping with the female confidence interval, then we'd say there is a significant difference between these two groups. And we don't have to do anything fancier than that. We just use the one sample confidence intervals to make that estimate. But if they overlap, you have to do a real two sample test. You have to actually use more sophisticated stats. So, and that's just summarized here. If you get these two groups, and so this here is an example where this is a 95% confidence interval for one group. Here's a 95% confidence interval for another group. They do overlap, but in this particular case, if you do a real two sample t-test, they are significantly different. So just because they overlap doesn't mean they're not significantly different. It doesn't tell you anything. So if they do overlap, then for sure they're significantly different. I'm sorry, if they don't overlap, then for sure they're significantly different. But if they do overlap, you have no idea either way. And that's what I'm just driving home here. That's why that is a significant p-value, even though these overlap. Okay. All right, so we're going to start talking about, in today's lecture, moving from one sample confidence intervals to two sample confidence intervals. So confidence intervals on differences. And then that is very much related to that linear regression example I gave you, where we're going to be focusing on is zero in the interval. So that will be the key thing we'll look for. But I don't want to dwell on that right now. We'll get there. Just to finish this review to make sure we get to the steady state stuff that we had to skip over last time. So transient simulations, the key thing for transient simulations of terminating systems is how many replications to run. That's the only thing that we can change in our experimental design here. And so we did a power analysis in homework H, and that's one way to handle this replication question. A little bit simpler way is what we did in Lab 9, and what we talked about in the last time is, well, if your stakeholder specifies a desired size of that confidence interval, and now we keep time with confidence intervals, so we know how to interpret them now. If your stakeholder says, I want my confidence interval to have this half width, then that, with a pilot study to get an idea of how much variance is in your sim, helps you figure out, solve for how many replications you need to satisfy that constraint. So those are two different ways you can use to decide how many replications you're going to run. And that's the formula we use for that. And we can even approximate the t distribution by z. And then this formula doesn't even have the number of replications in it. So as long as you run a little pilot study to figure out the standard deviation, you have your target half width from your stakeholder. You look this up in a z table, and then this will give you a bound on the number of replications you need to run. The number which you can subtract off the number of pilot replications you've already run. All right, so any questions about the transient case? It's pretty clear how we choose the number of replications for transient stims. Okay, so then we added on last time, well, how do we deal with steady state sims, where we're trying to estimate we only care about these data, which are a sample of the steady state behavior of the system. And so we not only have to decide the number of replications, but we have to decide how long to run the sim and how much data to throw out initially. And hopefully we want to throw out as little data as possible. So hopefully we can come up with a good guess for how to initialize the system so that the system is pretty close to steady state when we start it up. So, so the idea here, so we talked about intelligent initialization last time. So you can use real world data, you can use mathematical models from 470. So I'm going to focus here just on the warm up period and then the execution time question. And so if we assume again that initialization bias has been reduced to a negligible level, then at that point, we just needed to choose how many replications that we want to run. And we can do that using the same methods that we did for transient sims. But if you still have significant bias remaining, so you've used your 470 type math to predict what the steady state should be for the system, you've initialized the system at where 470 says it should be, but the nuances of the system keep shifting it away. And if you keep including that data, then it ends up biasing your results because they're not quite right from initialization. So increasing the number of replications will always decrease the confidence interval. It has no effect on the initialization bias. If you start in the wrong spot, if you've got data that are not steady state and you keep including them in your steady state, it's always going to bias your output. So what can we do? Well, we're going to discard a certain number of points from the beginning. And then how do we decide how to balance the discarded data versus the data we keep? And this is a simple rule. This is not guaranteeing that this is going to work for you all the time, but this is a simple rule to start with. And it basically is saying you take, so if n is the length of your total sim, so this is like the number of customers, or it's probably easier to think in terms of time. But if n is the length of your total sim and d is how much data you're excluding, then we kind of want the amount of data you're including to be at least 10 times the amount of data you're excluding. And that hopefully will give you a nice balance where you're throwing away just enough data to reduce the bias, and you're keeping a lot more data to hopefully, if there is bias, to kind of to have it sort of get dwarfed out or washed out by the steady state data, where there'll be like a lot of steady state data. To write that another way, the end time of the sim should be at least 10 times the warm-up period. So you start with that. That's a good starting point. Once you've done that, then choose your number of replications to be as high as possible. If you can afford 25 replications, then just run 25. But at that point, you're not going to get much more benefit from running more replications in a steady state sim. It will be better instead to extend your end time beyond this threshold. So we start with this threshold, and if we have the budget for running a sim this long for 25 replications, if that doesn't eat up all of our supercomputer time, then instead of adding more replications, we extend the end time. And I'll show sort of a picture of that here. So this is the idea here. This is our initialization phase of a sim, of a short sim. This is our data collection phase. And so we've reached that point where we've run 25 replications. And so now, instead of running more replications, what we're going to do is we're going to grow our end time. And that, if we keep this ratio at play here, that will also grow our initialization phase a little bit here. So we're going to run a longer sim, and we're going to discard a little bit more warm-up data. And the goal here is to, one, reduce bias more, because we're going to throw out some of this invalid data, and we're going to then add more data in. But the other interesting thing here is that because most metrics that you collect are averages, like it's the average wait time across customers, by extending the end of your sim, you add more customers to that average. If you're taking the average wait time in this replication, what happens to the variance of that average as you add more customers in? It shrinks. Right. So by making the sim longer, we will get less variance in our wait times coming. So in the average wait times, remember, this one replication runs, and then we run 25 of these. So we're going to have 25 average wait times. And then those 25 average wait times will form our confidence interval on wait times. Well, by running these longer, we reduce the variance in each per replication wait time average. So not only are we reducing our initialization bias, we're also reducing the variance so that we get tighter confidence intervals. So this is just as valuable as increasing the number of replications, but you get the additional benefit, it reduces bias. So that's basically the way I kind of did this example backwards here, is that if for a transient sim, if it was like, based on what I see here, I'd like to run 50 replications. But what this is saying is rather than running 50 replications, I know you'd like that. Like, let's take those extra 25 that you'd like to run and let's just double. Well, let's basically make it so that so this is the 50 you'd like to run. This is the 25 you've already run. So let's then double the initialization phase, and then with the end, and basically do the same thing with the end time. And so we're doubling the total simulation time and we're doubling the initialization phase. And that will give you the same benefit of running 50 replications, but instead of running the extra replications, it reduces the variance by extending the length of each individual replication, and that will reduce the bias as well. So once you have enough replications, increase the length of the replications, you do the same thing, but you also reduce bias. Any questions about that? So it's this relationship between the length of a replication and the number of replications. You can get, those are two levers to do the same thing, but it just so happens that lengthening a replication also reduces bias, whereas adding more replications does not. Okay, so that only works for steady state simulations, not for transient simulations. You're stuck with the length for transient. Okay, all right, now the other thing you can do is you say, well, let's think about this. For this last case here, I might make this really, really, really long. So I run a really, really, really long replication. And then now for every one of those 25 replications, I also have a really long warm-up period. So I throw away a lot of data. Well, an alternative to prevent from throwing away all that data, which is also time, because it takes time to generate the data you throw away. So an alternative, which Arena will try to do for you automatically, is to run an even longer replication. So basically take those 25 replications and run them in sequence, but only use one warm-up period. So if you run a really, really long replication, the idea is you'll have a warm-up period, and that will get things primed, and then you'll run a really long set of data collection. And then if you just arbitrarily stop and then pretend like this is a new replication at that point, if these batches are long enough, then the average waiting time for this batch will be independent of the average waiting time for this one. So if they are long enough, then one giant replication can be cut into pieces, and then each piece can be treated as an independent replication, and you only have to pay the warm-up period one time. If you go into Arena and you tell it to run a really long replication, and then you go into the report at the end of the sim, and you go into the per replication report, you'll notice that at some point, once the replications are long enough, you'll start getting confidence intervals in the per replication reports. And that shouldn't make sense to you. At first, it should say, that's weird. I thought a confidence interval can only be generated across replications because you only know that replications are independent from each other, but they're not independent within. What Arena does is if it runs this long enough, it will try to create batches for you, and it runs some math behind the scenes to try to say, is this batch that I've created independent of this next batch? And if it can infer that one really long replication has independent batches, it will then create these faux replications for you, and it will generate those confidence intervals at a per replication level. And this is why for steady state sims, sometimes you only run one replication, and you just run it really, really long, and Arena will generate all the confidence intervals you're used to for multiple replications using this batching, and it does it totally automatically. Now, if you happen to see it's say, a replication not long enough, or correlation, too much correlation, things like that. If it would, in the per replications, if it refuses to generate a confidence interval, then that means that it tried to batch things up, but things were not long enough for it to have evidence of independence, and so it did not even bother generating the confidence interval. So that's what we mean by batch means. Well, there are questions about that idea about batching and why batching is good, because it prevents you from having to do this 25 times. You only do this once, but then you do the rest of this 25 times. Okay. So how does Arena do that behind the scenes? You've got the output analyzer actually provides you a little bit of the tools, a window into those tools that Arena is doing behind the scenes to figure out if it has, how it comes up with these batches. So in the output analyzer that you've used now since Lab 9, there is a parallelogram. So I took replication 1 of the Lab 9 manufacturing system. And I took did a parallelogram of, this is work in progress, it looks like. So I said, well, what's the whip? If I look at the whip, you can measure the whip at any particular time. And what the correlation here, the parallelogram does, is it says if you look at a particular whip at any one in particular time, how well does it predict the whip at times afterwards? And this is saying here that if you look at a whip that is separated by a very little amount of time, you get a high correlation, so a high positive correlation. So if you know the whip was, if there were 5 work in progress, a second later, there's probably still 5. 2 seconds later, maybe there'll be 3, but it's still just going to be close to 5. That's what we're kind of seeing here. Now, this gets smaller. Sometimes it goes negative, and this might be significantly negative. So this might mean if you go 20 lags later, so 20 samples later, 20 seconds later, then it might be flipped. It might be, well, if it's 5 now, then it might be -5 later. I mean, whip wouldn't be negative, but it's, it can go that direction. Now, notice like here, there's very little autocorrelation. So what I hope you're seeing here is that in many systems, you're going to get high correlation early, and then low correlation, sort of a background level of correlation here. And if this is small enough, then we can maybe say that there's a correlation length that is, let's say, like once you're beyond this, whatever, 30 seconds or something, at that point, 30 seconds away, the whip now is independent from the whip 30 seconds later. And at that point, you can say, well, maybe I can just batch things, and every 30 seconds is like a new simulation. And you can generate these in MATLAB as well. So this is a parallelogram in MATLAB, similar idea. MATLAB's nice enough that it actually puts the 5% confidence or the 5% thresholds here. So when I look at this in MATLAB, I see that there's really high correlation for 0 lag. Well, that should make sense, because if I know the current value, I can predict the current value. It's saying immediately afterwards, there's pretty high correlation. But then shortly after that, it gets buried in this blue envelope. So this is kind of telling me that maybe once I hit around 20 lags, so every lag is like a sample, so that's like 20 seconds if it's 1 sample per second. Then after that, I can consider that any distances more than 20, they're independent of each other. So I could create a batch that at a minimum was this size here. Now, I normally want some safety factor. We love safety factors in engineering. So let's multiply that by, 10. So if you detect that you have correlation that goes into the insignificant level, so it's just random correlation at that point, then you could say, oh, well, whenever that happens, say 20 seconds, that's my correlation length. I'm going to multiply it by 10, so I'll make a batch size of 200. This is what Arena is basically doing behind the scenes. And so if you give it a replication of 1,000 minutes, and it manages to predict a correlation length using this type of math of 100 minutes, it might multiply that by 10 and 1,000 minutes, and then it says, do I have enough total time to generate replications that to generate batches of length 1,000? And if it does, it will generate those batches and generate confidence intervals for you. If not, if there's correlation throughout your whole replication, then it'll give up and say, I can't generate a confidence interval. But that's what's going on behind the scenes. All right, questions about that? The parallelogram, this idea of correlation in steady state and getting rid of it. Okay. All right, so that catches us up. So there's only a little bit we have to add to this before we finish this unit. So we've talked about absolute performance so far. So how do I estimate the actual wait time coming out of my sim? Well, now I want to compare two sims. So how do I do a relative performance of these two systems? So idea here is I've got, let's say model system one, model system two. So system one, this is maybe our as-is system. It's a call center. So people call in, they select whether they want to go to billing or whether they go to support. And we know that based on you do the input modeling, roughly 60% go to tech support and 40% go to billing. So then there are agents that are trained just for billing, and there are agents that are trained just for tech support. So there are 3 operators here for billing, 4 for support, and we can measure metrics for the callers, like how long did they wait in line? How long did it take them to get out of the call tree? All of those sorts of things. Now, a manager comes and they say, well, what if we cross-trained? What if we train all of these agents to do both billing and support, and then we can just send them here? Now, why might they want to do that? They might see that the utilization of billing is really low. So you've got a bunch of people waiting for billing calls that if they knew how to do tech support could be helping with tech support, but they're not. So then they do cross-training. And in Arena, you can implement cross-training with resource sets. In fact, there's a call center example we did a couple labs ago. You can see an example of how they use resource sets to do exactly this. So resource sets are really cool. You can sort of say these resources are priority. Their priority are this job, but if you call a resource set that has a bunch of resources in it, you're saying those resources could theoretically do another job as well. And you can then ask for resources out of the set as opposed from the resource group. And that's how you can implement cross-training. So you've got these two systems, your cross-train system and this system, and you'd like to see, is there a difference in, let's say, wait time for the caller? So you basically are going to have these two tables. So system one, you ran a certain number of replications. System two, you ran a certain number of replications. From those reps, you're going to get a mean for both systems and a variance for both systems. So you could conceivably generate a one sample confidence interval for both systems and compare that. But are there other things that we could do? And the thought here is, what if we generated a effectively 2 sample confidence interval? What if it's a confidence interval on their differences? And so that's what I've modeled up here. So this idea here that instead of saying it's y1 plus or minus a half width and y2 plus or minus a half width, I'm saying it's the difference, y1 minus y2 plus or minus a half width on the difference. And so if we were to generate this 2 sample confidence interval, then we could say is 0 in the 2 sample confidence interval, just like I was talking about with the linear regression problems. And so if the confidence interval was totally over on this side of 0, so 0 is not in it, then we can infer that the system 2 metric is significantly higher than the system 1 metric. If on the other hand, it's on the other side, so 0 is not included, so we can now conclude that the system 1 metric is significantly higher than the system 2 metric. But if 0 is included, we can't say anything. We're saying it is very possible that these two systems are the same, but it's just as possible that even though the average is above 0, that might have been just total luck by these numbers that came out of my sim, and it is still totally reasonable that the real system is actually on the other side of 0. So we can't say anything. We can say that there is not enough of an effect between the two systems for us to detect it with this number of samples. So if we increase the number of samples, we make a smaller confidence interval, maybe we can start detecting it. All right, so that's the basic idea behind this. Now, what we're going to talk about for the rest of the day here is how you set up this experiment determines how you set up this half width. Every half width you set up will have this formula, which is why I tried to emphasize this formula to this point of so far. It's going to be a standard error of this mean, a standard error of the mean difference, times a critical t value where the degrees of freedom are going to be the thing we care about. So depending on how you set your experiment up, we're going to use different standard error formulas and different degrees of freedom. But the confidence interval will have the same formula. So the experimental setup sets up the confidence interval formula. Once you have the confidence interval, you can interpret it like this, regardless of how the experiment was set up. So that's where we're going. All right, so the three approaches, we've got a paired approach, similar to what you already did in homework H, and then two independent approaches having to do with whether your two populations have the same variance or different variance. So that's what we're going into. So this is just a summary, a table of contents of what's going forward. So I don't want to spend too much time on this because we're going to see this again in the next unit under variance reduction, and you've already practiced this in homework H. So if you can pair your two systems together and run them with the same inputs, you can create blocks based on those inputs and take differences per block. That's exactly what you did in the first question. I think the first question of that homework H. And so this is this idea here is basically the confidence interval version of the paired difference t-test. So we create the same number of replications per system. We use the same input for both systems to generate differences between the systems. And why do we do this? Because if you take the variance of a difference, then after you go through a little bit of probability, you can derive that the variance of the difference between two systems is the variance in system one scaled by the number of reps, plus the variance in system two scaled by the number of reps, minus the correlation between the two systems scaled by the number of reps. So what this is telling you, this correlation coefficient here, is if you can increase correlation between the two systems, you can decrease variation in the estimate of their differences. And that's great because that means less replications. Less variance means less replications. So if you can give them both the same inputs, so I've got this set of callers coming into my two call centers, and it's just, this is a difficult day. This is a hard day at work. This is an easy day at work. If the hard day at work for system one is also a hard day at work for system two, and the easy day at work is easy for both systems, then there's going to be a correlation across your batches of callers. All the hard days will be hard for both. All the easy days will be easy for both. And that variance across the callers, we can subtract out by putting them all on a level playing field. That's what this math is telling you right here, is that if the inputs are correlated, then we can control for the correlation in the inputs and subtract off that variance. And that means we can run less replications. That's the essence of why we block, why we generate this. And so this is what you did on that homework. You create differences per block. You calculate a mean difference. You calculate a standard deviation of the difference. Your standard error is a standard error of the differences. Your degrees of freedom are r minus 1 because you had to burn 1 degree of freedom to calculate this standard deviation. And that gives you your confidence interval. It's your mean difference plus the critical t-value with this number of degrees of freedom times your standard error. It's exactly what you already did on the homework. And you can generate a confidence interval where now we just have to ask, is 0 within this confidence interval? All right, so that's the easy case, the case we've already seen before. Any questions about that? The paired case. You can only do that if you have control of your inputs and you run the same input into the two simulation models and generate differences per block. Okay. All right, so now what if we can't do that? Now we've got system one, it ran with its own replications. System two, either we couldn't get a correlation. It might be that easy days for system one happened to be intermediate days for system two. There was no correlation across those inputs, or just the way things were run, it was impossible for me to run the same inputs into the two systems. One system is a real system, one system is a sim system. It's just impossible for me to do the blocking. I can't do a paired design with those anymore. So I have to consider them as independent systems. So I have to do, a real two-sample t-test confidence interval. And so my question then has to be, for a parametric test, I need to know something about the variance of my two hypotheses. And so for a one sample t-test, I just assume that the variance is the same between my hypothesis and the alternative, but I don't really have to worry about it because it's only a one sample, so I really only have data from one system, and so it's an easier thing to assume. But when you're actually comparing one simulation which has its own variance and another simulation which has other variance, if this is a tight simulation that's very repeatable and this one's a very broad simulation, it then creates some ugliness in how to do the t-test between them. So if I'm lucky, and so by lucky I mean this is going to give me the highest power, if sim A, so the as is system, the system where we have two separate types of support rep, if that has the same variance in its outputs as sim B, where things are cross-trained, then I get more power, and I'm going to do what follows here. Now, I think this is covered in 380 or 385. How do I tell if two populations have the same variance? Has anybody had a class where you do a statistical test for variance equivalent? What was that? I hear it whispered. I hear a lot of correct answers being whispered. So speak up. F-test. F-test is a great way to do it. F-test is what underlies the ANOVA. The Levine's test, that's another test, is a great way to do that. So I'm not going to make you do an F-test or a Levine's test in this class, but whether you do this or the next one that I'm about to present depends on the output of that test. So you have to look at your two systems and do an F-test or do a Levine's test and test for equivalence and variance. If you get equivalence and variance, Levine's test, I think, is higher power than an F-test. F-test is really looking for differences in variance. Levine's test is looking for sameness in variance. So if your Levine's test confirms that these two systems have the same variance, you can do a pooled variance two-sample t-test. And so what you do there is you basically create a shared variance. You allow the two systems to have different means, but when you calculate the estimate of the variance, you use both of their differences from their means to calculate a joint variance. And so this is the formula for that. So you can calculate the variance of your individual systems. This is the variance of your pooled system. So you've calculated the individual variances, and this basically groups them together. Because you had to calculate two variances, one per system, you burned 2 degrees of freedom because you had to estimate a mean in both cases. So that's why the degrees of freedom are the number of samples from system 1 plus the number of samples in system 2 minus 2, because the 2 that you burned, one for system 1 and the other for the system 2. Seth Meyers reference, I guess. Anyways, so that's your degrees of freedom. And then you can estimate your standard error of the mean with this formula, which this is a relatively, I think, simple formula to kind of work through. This basically is saying that your variances are additive. So it's saying here that the standard error of the mean, if you take this standard deviation and pull it inside here, then you just see that it's the standard S squared that you got up here. And you just sort of divide it down by the replications in system 1 and divide it down by the replications in system 2, add those two things together to get your variance, and then take the square root of that to get your standard error of the mean. So it's a relatively simple formula for standard error of the mean. It's a relatively simple formula for degrees of freedom. So with this, we now can calculate our two-sample confidence interval, because we know this, we know that, we can plug that into that formula. So we can then go and do exactly that test. Is 0 in that confidence interval? Now, what if it's the other case where we have unequal variances? Well, then we have to use Welch's t-test. So Levine's test comes out. It says, I detected a difference in variance. That system is more repeatable than that system. At that point, you have to use a lower powered two-sample t-test, the Welch's t-test, and we can't pool the variances. We have to keep them separate. So now our standard error of the mean here, or our standard error of the difference here, is just basically going to be the variance we detected in system 1 plus the variance we detected in system 2 and the square root of that. So the standard error here is pretty easy. It kind of looks similar to the one we just saw. But So this is not the formula that is ugly. Again, this is just, again, variance of system one, variance of system two divided by their mutual number of replications. Square root of that, that's the standard error, the difference. The tricky part is the degrees of freedom. Now, this is an ugly formula, and it's outside of the scope of the class to go into the details here. But basically, we're saying if this was a chi-squared distribution, you can solve for what degree of freedom would you need for the chi-squared distribution to match this. And it turns out that it's this ugly formula here. So you don't need to know the background behind that, but that's why this has this ugly formula. But you can write this down. You can store this somewhere. It's not hard to calculate. It's just ugly to look at. But now you have right there. You've got the standard error for the difference, and you've got. Did I go the right way there? And you've got the degrees of freedom. So with that, you can now calculate a confidence interval based on Welch's t-test. So in all three of those cases, you figure out the standard error of the mean, you figure out the degrees of freedom, you calculate a confidence interval, and then you compare the confidence interval to 0, and that will tell you if your two sample test tells you if one system is better, the other system is better, or if you can't tell the difference. Any questions about that? Okay, so we'll finish up the rest of that next time. There's only a little bit of Bonferroni to talk about. So let me give you a short answer. All right, so Welch's t-test is for the case where you have equal or unequal variance. Those are the only two answers I'll take, equal or unequal. If you give me another answer, it tells me that you're not actually here right now and you're using keywords from the lecture to put in there, and it'll give you a 0 for today. So unequal or equal, Welch's t-test, is it for unequal variance or equal variance? And otherwise, we'll see you Thursday.